Today we will have a closer look at an electrophilic aromatic substitution. It is in this case an acid-catalyzed Friedel-Crafts alkylation. So what do we need for this kind of reaction? Well, we need the acid in catalytic amounts, the proton, and bound to the corresponding anion, then cyclohexene, and in this case methoxybenzene as a rather activated aromatic, electron-rich aromatic system. Methoxybenzene usually is called anisole. So this is the starting situation A, and we want to develop an energy reaction pathway diagram, and we have to start at a certain energy level. We choose simply this here. This is then the situation energy level for the situation A, and we should keep in mind, since this is an exothermic reaction which runs just smoothly and nicely for the production of here the product E, then the energy level of E should be energetically downhill. So energy level of A should be above E. Well, in the first step, the proton, the acid, will protonate either this molecule or that. Well, it will much faster protonate the methoxy group with the free electron pairs. However, this is some kind of chemical dead end. It will be protonated and it will be deprotonated again. So it is not important for the outcome of the reaction. So we will just skip that and have a look at the protonation of the olefin. Then we will get to this secondary carbocation with the anion in close proximity. This is then situation B, and this is an reactive intermediate, so it goes energetically uphill. Here we are at the situation B. It is a reactive intermediate, and we get to this intermediate through a transition state, a bit higher in energy, and then this bit lower, the reactive intermediate. So if now anisole is approaching, then there will take place some electronic interaction. Well, you can compare that to some kind of solvation. This cation will be coordinated to the high electron density here. At first, not destroying the aromatic system, since this is a stabilization. The situation C, this is then called a pi complex. This is a stabilization, therefore we should go a bit downhill in energy to situation C. Then the sigma bond is formed from the ortho, or preferentially from the para position out of steric reasons, a sigma bond between this carbon and that electrophilic carbon. Here we have the result. This is the sigma complex. It is stabilized through a couple of mesomeric structures. This is just one mesomeric structure with a cationic charge here in this position. Then if that double bond migrates, this is another, then mesomeric structure with a positive charge here, then we could formulate one with a positive charge there, and of course also one with a positive charge at the oxygen, because the free electron pair can also participate in the mesomeric stabilization of that cation. Well, I have abbreviated with just those mesomeric arrows here. So it is stabilized, however, by mesomery, but also, of course, inductively. But although it's stabilized, it is de-aromatized and therefore even higher in energy. This is then situation D. We have it up here. Well, and now the next step is rather simple. We have the counteranion still in close proximity. It can then deprotonate here, just grab that hydrogen, remove it, and through this process the aromatic system is restored and we are at that product. This is product E, and as I said, it is then in this whole scheme the situation which is energetically the most favored one, this one here. Well, okay, how is the structure of that if we have it in terms of the conformation? We have here a cyclohexane moiety. This will adopt a chair conformation, and this arrow substituent will be preferentially in equatorial position to avoid the 1,3 diaxial interaction with the hydrogens if it would be in an axial position. So this is the preferred conformer. Thanks for listening.